Okay, so in the last video we talked about some of the basics of waves, how to classify them, what a wave is. We talked about mechanical versus electromagnetic waves, transverse versus longitudinal waves, and then the different parts of the transverse wave, including the crest, the trough, the rest position, that middle line there in the middle, and the different parts of the longitudinal wave, the compression, refraction, and then the wavelength, which is basically defined the same for transverse waves and longitudinal waves. It's the length from one point on the wave to the next corresponding point on that wave. And we also talked about what frequency is and how to measure frequency. So now we're going to see the wave equation. Okay, and so you can read what it says on this slide, but I'm just going to write down the wave equation. Now, there's only one equation in this whole unit, and so it's kind of important. It's a very simple equation to use, but this is what the equation looks like. Okay, V equals lambda times F. Okay, now in the last video we talked about lambda, this upside down looking Y thing. This is the symbol for wavelength. And remember, wavelength is measured in meters typically. It could also be in centimeters or millimeters, inches, feet. That is a unit of length. Lowercase f is the unit for frequency. Remember, that is the number of waves passing a point per second. Okay, that's typically measured in hertz. That's Hz. Okay, this is typically measured in meters, although not always. And then v is what's called the wave speed or the wave velocity, either one of those, depending on what the problem says. Okay, and wave speed or wave velocity is measured in meters per second, or centimeters per second, or something else like that. And this is what's called the wave equation. Okay, wave equation. And again, as far as I can remember off the top of my head, this is the only equation in this whole unit. So it's kind of important that you understand the different pieces of it. There's not a lot of calculations in this unit, but the calculations that you do see typically involve the wave equation. Okay, so wave speed is equal to the wavelength times the frequency. Now, in the last video, we talked about how wavelength and frequency are inversely related to each other. In other words, the higher the frequency, the lower the wavelength, and vice versa. And you can kind of see that borne out in this equation. If you have a set wave speed, if the left side of this equation is fixed, right, if you have a higher frequency, in order to get the same value, you have to be multiplying by a smaller number. So again, as the frequency goes up, the wavelength has to go down, or vice versa. Okay, so now we're just going to do some basic examples and putting together everything we've learned about so far. So pause it here if you need to. I'm going to erase this slide. Okay, so example 1 says a wave is measured to have a frequency of 60 hertz. Okay, so this is the frequency. Remember, Hz is pronounced hertz. Okay, it's named after a guy, actually the guy who discovered radio waves in the late 1800s. And so I'm going to write down my first given as F equals 60 hertz. If the wavelength of the wave is 0.24 meters, okay, so that means I have the wavelength, that's lambda. Okay, the Greek letter lambda that looks like an upside down Y is 0.24 meters. I want to know the wave speed. So this is a super easy equation to use, the wave equation, V equals lambda times F. So all I have to do here is multiply. Okay, so I take my equation, lambda is 0.24, and multiply by the frequency, which is 60. Okay, and so I'm going to get my calculator out. And again, there's only the one equation in this unit, and so definitely make sure you understand how to use the one equation. And if you do it correctly, you should get V equals 14.4 meters per second. Okay, so that is example 1. Very basic example using the wave equation. So pause it here if you need to look over that some more. Okay, so I'm going to erase. Take a look at example 2. Example 2 says a wave is traveling with a speed of 150 meters per second to the right. Now, just based off of the units, I know right away that this has to be V. Nothing else in this unit has units of meters per second except for wave speed or wave velocity. Now, the first one says find the wavelength of this wave. Now, your first instinct might be to say, oh, I should just use the wave equation and solve for wavelength. But the problem is I actually don't have the frequency. I do have V is 150, but I don't have the frequency. Okay. In fact, the next question asks me to calculate the frequency. So you might be confused for a second, but if you look over here, we actually have a picture of the wave, and from the picture of the wave we can find the wavelength. Now remember, the way you measure wavelength is you pick one point on the wave and you measure the horizontal distance until you get to the next corresponding point. Okay, so for example, if I pick the start of the wave, which is at x equals 0, and I keep on going until I get to the next corresponding point, that would be over here. Now you might ask, why isn't 4 a corresponding point? Well, because if you look, the wave is going to repeat itself eventually. At this point, at the beginning, it's going up and then down. So when you get to 4, it might still be the same point, but it's not the same corresponding point because now the wave is about to go down. You have to go all the way out to 8 here. Okay, so I would say from the picture, from the diagram, I would say lambda equals 8 meters. Okay, sorry, that's a lambda. And the unit here is meters. That's what it says. Okay, so I now have the wavelength is 8 meters from the picture. And so now I can plug in and get the frequency from my wave equation. Okay, so to get f by itself, I need to divide both sides by 8. So I do 150 over 8. And again, the unit for that is going to be hertz. So 150 divided by 8 is 18.75. So F equals 18.75 hertz. Okay, so that's a problem where you not only have to use a wave equation, but you also have to understand the diagram that you're looking at. This is, of course, a transverse wave based off of what it looks like visually. Okay, so pause it here if you need to. We have the two answers for example 2 right here. Okay, so I'm going to go to the next slide. Now the next thing we're going to talk about is amplitude. Okay, the first bullet point right here tells you exactly what you need to know about amplitude. The amplitude of a wave is directly related to the energy of a wave. And if you think about it, that's probably kind of common sense, right? Amplitude, if you think of a transverse wave, amplitude is basically the height of a wave. And so if you think of going to the ocean, or you go to the beach and you look at the water coming in, the higher up it is, the more energy the wave has. I mean, that's basically what this slide is saying. Okay, the amplitude of a wave is directly related to the energy of the wave. Okay, and on this diagram here, this picture here, you can kind of see the difference between higher amplitude and lower amplitude. Okay, this is a lower amplitude, this is a higher amplitude. And so basically all we're doing is we're looking at the height of the wave. So this is a transverse wave. I want to focus on the transverse wave because this is the most common type of wave. We have the different parts now. We have the crests at the top, the troughs at the very bottom. The amplitude is measured from the rest position, that midline, to a crest or a trough. Now it's very important because a lot of the time you'll get problems asking you to find the amplitude. You always measure the amplitude from the rest position in the middle. Okay, you're not measuring from crest to trough, you're measuring from the middle of the wave, either up to a crest or down to a trough. So in other words, from here to here, this vertical distance, okay, that is the amplitude, A. Okay, that's what affects the energy stored in the wave. Now what's not shown on this diagram, of course, is the wavelength. If we wanted to, we could also add the wavelength to this diagram. We could say, oh, this is the wavelength right here, from one point on the wave to the next corresponding wave. The next corresponding point. We can also go from trough to trough or whatever we want to do. Okay, lambda. Okay, so those are the different parts of a transverse wave. Now pause it here if you need to, and then we're going to do a couple more examples. Okay, so example 3. Basically, we're asked to take a look at this picture and answer the questions using the picture. Okay, it's a multiple choice question. So 6, it says this letter represents the wavelength. Okay, so remember, wavelength is a length that's always measured horizontally, and so we only have a few options here. Take a look at A. Remember, the wavelength is the horizontal distance from one point on a wave to the next corresponding point. A is a wavelength, okay, because it's going from a crest to another crest. If you look at E, it is a horizontal distance, but it's not between two corresponding points. It's actually the horizontal distance between a crest and a trough. So E is out. C is also out because these 2 points are not the same point. They might look like the same point, but they're not, because here the wave is about to go up to a crest. Here the point is about to go down to a trough. Okay, so these are not the same corresponding point. And so the answer to number 6 is A, just A. 7, this letter represents the amplitude. Remember, the amplitude is always measured from the rest position, okay, from that midpoint. And so if you take a look at B, B does not represent the amplitude. It actually represents twice the amplitude because it's going all the way from the crest all the way down to trough. So the amplitude is actually going to be D, okay, over here. It's from the trough to the rest position in the middle. And then the trough is at G, and the crest is at E over, or not E, I guess it's F over there. Okay, so pause it there if you need to check your answers. Then I'm going to go to the next one. Okay, example 4 says wave A and wave B have the characteristics shown in the table, and we're given the frequency, amplitude, and wavelength of wave A and wave B. Both waves are sent through the same spring. Which wave has the greatest energy? Okay, so pause it here and see if you can figure this out. The key word there is energy. Okay, so remember we talked about this a few slides back, but what affects the energy of a wave is the amplitude. Okay, and that is the only factor that affects the energy stored in a wave. And so this is very simple. Whichever wave has the greater amplitude, which is wave A, has the greatest energy. Okay, so the answer there is A. Okay, pause it there if you need to. And then example 5. I think this is the last example we're going to do in this section. It says for the wave shown to the right, answer the following 5 questions. So you should have 5 answers for this, basically. Okay, so pause it here, see if you can figure out the 5 answers to this question. Okay, so what type of wave is this? Well, this is a transverse wave. We can tell that right away just by looking at it. Remember, most waves are transverse waves. In a transverse wave, the particles are moving perpendicular to the direction of the wave. So here the wave is moving to the right. We can tell that because there's an arrow going to the right, but the actual particles are moving up and down. And just from the shape, we can recognize this as a transverse wave. Now, the amplitude of the wave is always measured from the rest position. And so the rest position is here at 0. The wave goes up to 1 and down to -1. So the amplitude, I'm going to write it out here, A equals 1, and it's actually 1 millimeter because it says millimeters right here, mm for millimeter. Okay, so that is the amplitude. Now, the wave speed is given right here. Okay, we don't have to use a wave equation or anything, it's actually given. Okay, so V equals 200 meters per second. The wavelength we can directly measure just by picking one point on a wave and measuring the length to the next corresponding point. So I'm going to do from this crest to this crest, from here to here. That length is 2, and the unit for that is meters. So lambda equals 2 meters from the diagram. And then using the wave equation, I can easily calculate the frequency. I have V equals 200. Lambda, the wavelength, is 2. And so all I have to do is divide both sides by 2. And I get the frequency is 100 hertz. Okay, so now you should be able to answer everything on your first worksheet. Keep in mind that you need to know the different parts of all the different waves. You need to be able to classify different types of waves, do calculations with a wave equation, and answer questions that combine graphs like this with a wave equation. Okay, so pause it there if you need to finish looking over that. Please let me know if you have any questions. Again, you should now be able to do worksheet number 1, doing basic problems with wave properties and the wave equation.